also raise that? I'm gonna use the blackboard. I don't even need this, I'm loud mouth. Only on the radio. Well, I'm gonna try to run this somewhat like a radio show, in that I'm sitting there looking at you 5 guys in the brain trust, actually 4, sometimes 5 in the studio with Bruce on the phone, and I gotta juggle all of them, come up with questions, get the commercials on, and man, oh man, is it a Chinese fire drill. You gave them the first question already, but that's all right, they read it, we'll read it to them. They said, oh, you're gonna put it up there, okay. I had one quick question before I start, because I can't lecture you guys on anything. There's no way I'm the lecturer, believe me. I'm here to ask and learn, and so I'm gonna just set some rules for tonight. Adrian is gonna help me. Mr. McPartland and possibly Mr. Murdoch, I'd like you to be our arbiters. Perhaps if Jerry were here, he would be one.
And Dr. Dave Carey is here.
Is he good?
We'll make it work, yes.
Know some stuff. That's too many brain trusts. Would you leave, Dave? I can't handle it. So in other words, I'd like you guys to be the final arbiters on any of these questions. And the rest of you, I kind of want to tease you and pick your brains and see if you know as little as I do, because you're going to eat me alive. Actually, I thought of a real quick one from the show we just saw on the planetarium. You know where it said they're looking at stars that wobble? Is that always from a side view? The only time we can see a transit or a wobble is from the edge of their solar system, right?
Definitely for a transit, but for the wobble, it doesn't have to transit. It just has to make a motion in the radial line between us and the star.
Okay, if we were looking down on the solar system, if it was like this rather than like this, if you were up above our solar system looking down, would you see their star go like this? Could we see it?
Not unless it was enough that you could, see the angular displacement visually, but you wouldn't get it from the spectra.
Okay, get ready to turn this over. Appreciate that. We're going to get to eating early. Would you take the first one over?
I'm going to turn the projector down here.
Okay, thanks.
So I can find my...
It's a Wookiee.
Bard Galaxy, is that my first one?
Yeah.
You've seen them. Let me finish the rules. If I make a mistake, you're welcome to yell out and tell me, correct me. Otherwise, let me get it mostly out, and then we'll have a give and take. Bar galaxies, when I first saw one, it made me wonder, how in the world do the stars crammed into the bar, assuming, and I'll ask this right away, the whole galaxy is turning, right? Does the bar turn? Do they know what can they see from a distance and have enough time to determine that that bar in about a few million years is going to be like this?
Yeah.
And then like this. Are they full of stars?
Yeah.
That's, yeah, it does look like one. At any one time, you can see that, I'll just paraphrase, I know what I wrote up there. At any one time, this thing appears to be full of stars, and they're turning as a solid bar unit.
No.
They're not. Okay, then let's go right to it.
Okay,
Yes, ma'am.
Joanne's gonna answer.
I think that the action, and I should say, this information could be like a decade or so out of date, but my understanding is that the stars in the bar orbit in something which is called a box orbit, which isn't mean it goes in a box. It means that every individual star is doing a complicated around and up and down and around kind of motion, but back and forth and up and down. And it's doing something as complicated as that because it's not like a simple orbit where you have the sun in the middle and a planet goes around. Each individual star is orbiting with the gravity of all the other stars, but when you do out the math of all of that, it ends up that they end up confined in pretty much a boxy space, but the box must rotate. Mustn't the box rotate?
Have any of you
The
ever
box
heard that
must
before? A
rotate.
box?
Box orbit.
Box orbit.
Yeah.
Do we have a bar going in our galaxy?
Yes.
So are we seeing stars that do what you just said? They're,
We do that, we go up and down as we go around. It's-
yeah.
We're
Although
not as
we're
restricted.
not in a box or, yeah, you look at something like Aldebaran, Aldebaran, which is a halo star in our galaxy that happens to be passing.
Arcturus.
Sorry, Arcturus.
okay?
Arcturus is a nearby star that happens to be in our part of the galaxy, but it's not moving the same way most of the other stars around us are doing. It's just whipping through on a completely different path.
Does science know why it happened? Why that?
Because
why
it's
that-
not really part of the disk population. So we have the disk where all the spiral arms are. But then there's the halo population, which is more like a big spherical region.
In and out of the black
So
void.
coming out, going into the black part. If you look at it edge on, it would look like, you'd still see it as a sphere.
So it's safe to assume that this bar is crammed with more stars than, let's say, out here.
Most of the stars in the galaxy are in the bar.
Is that right?
Yeah.
So they're kind of like, what are the globular clusters, right? They're all,
It's certainly denser than, yeah, it's a lot denser than out here. We're up in the boonies.
It's a hot dogular cluster.
Yeah.
okay. And so the ones in the middle are going super fast because there's a black hole there usually, right?
Really close, yes.
Okay.
Once you get a little ways away from that central black hole, speeds are pretty much constant all the way through.
But we are out here somewhere in this little
Yeah.
Orion.
We're up in the boonies, yeah, about halfway out.
Give me the honor.
Was there something Chuck keeps mentioning about the arms of the galaxy don't really change. It's kind of like a traffic jam. The stars bunch up there,
Yeah.
but they pass through,
Yeah.
and then they're out of that traffic jam.
Stars are going up.
But that traffic jam just kind of stays
The
there.
spiral arms are really, what you're seeing there is not lots of stars. It's not the biggest group of stars in the disk. You're seeing the brightest stars in the disk. There are just as many stars between the spiral arms as there are in the spiral arms.
Oh, weird.
But the spiral arms are where stars are forming.
But we pass through those spiral arms.
We go through them, yeah.
But so we'll be our solar system will be passing through a bright star system that's kind of more cloudy and where stars are formed.
It's not
and then
that we're passing through, they're all in orbit, it's that they go through situations where things are a little more compressed and a lot more young stars are born, which tend to be big, bright, tend to include big, bright ones that wink out fast. And then the whole route moves on, it's a little less dense, there's less formation, the young, bright ones are gone.
Because they
Because-
die.
So
They
you're
die
talking about a
fast.
whole new type of orbit. It's not around
It
anymore.
is around.
Yeah.
Yeah.
It is
We're-
around.
I was talking about the box orbits in the middle,
That's
the
what I'm
ones,
talking
yeah.
about.
Yeah, those ones are.
This is, no, he's talking about.
So out where we are with the spiral arm, we're out in the disk, we're doing something more like a traditional, nearly circular orbit. There's a little up and down wiggling going on there, but it looks a lot like the way we tend to think of an orbit. It's just going around the center.
Okay, well, before we leave this subject, I want to just, I'll draw another real quick, but then you're not going to believe what this thing is. Which way do you think that galaxy is turning?
The stars
Clockwise
are
or
going that way.
counterclockwise?
Stars
Huh?
are going that way.
Okay, well, according to a certain outreach coordinator I know and hang around with, it could be going either way. Is that right?
And there are some where they're going both ways, that seem to be mergers of galaxies.
It's trailing behind these arms of stars, and yet it's going in that direction counterclockwise? Are you kidding me?
Well, because they're like traffic jams, they're not like a solid object.
Well, I've seen computer variation, or computer, what's the word I'm looking for? Demonstrations, yeah, where the inside turns a little faster, and the arms just keep trailing behind and trying to catch up, and
Yeah, but then it would wind up and go away over time, see?
Yeah.
I haven't had enough time.
That's where the whole thing about
No,
dark matter has
yeah.
come about, because the arms don't do what you just said. The radial velocity of the arms as you go off from the center should be going down and down. That's the reason they bend.
But they don't.
But they don't find that.
Yeah.
Speaking of
Arms,
There's
don't
one is uniform disk.
Don't confuse the arms with the stars. The arms are not the stars.
They're full of stars.
But their stars are coming and going through them all the time.
Okay.
The arms are not defined by any group of
Our
stars.
solar system's gonna wind up in a big arm someday?
It's gone through. We've been around the galaxy 20 times. We've gone in and out of spiral arms many times.
Is it safe to say that the inner stars are going faster, just like Mercury goes
No.
faster,
Nope.
than the outer stars? It's
That's the
not,
whole thing about dark matter.
it's the dark matter?
Yeah, if it was a uniform disk and it was governed just by gravity, which you just said would be the case, but they're finding that all the stars in the galaxy tend to go at the same rate. It's like a big disk that's turning.
Okay,
Yeah.
speaking of dark matter, would you flip the next page over?
Oh, yeah.
Dark matter. If it has mass, it weighs something, but we can't see it, enough to add all this bulk to the galaxy, why doesn't it also obey our regular matter laws of physics?
It does.
In other words, why doesn't all the dark matter clump up together in balls, spheres, just as the countless stars, planets, and moons we see do? Are there possibly new theories out there that perhaps it does, and all that dark matter are just billions of huge, larger, invisible globes around planets and stars we now know?
But
We see that are obeying.
That's what I would do.
what we see of these, putative particles that make up this dark matter is that they don't interact with each other much. So you gotta interact to stick, right? Matter bumping into other matter has to do something to stick, otherwise they just kind of pass on through each other. And that's probably more electromagnetic forces than anything else, but dark matter doesn't seem to respond to electromagnetic forces. And so the particles, they may slow down a little gravitationally, but they don't slow down as much as they would if they actually collided with each other and did things. And so you don't tend to, it clumps, but the clumps tend to be fluffier. That's my understanding of the whole thing.
That's right.
We have four forces in nature. The two that we're familiar with are electromagnetism and gravity.
Right.
The other two involve atoms. Are you saying that in the dark matter world, the electromagnetism isn't there?
Right.
Bingo.
And therefore it doesn't clump into balls?
That's right.
That's the reason?
That's the real key to dark matter is it doesn't respond to electromagnetic force. We already know of particles that do that. Okay, neutrinos. Neutrinos ignore the electromagnetic force. They don't. We know lots about them. Dark matter's behaving that way. It's what they call a weak force particle.
Okay.
But, and like neutrinos, it'll go through stuff. It doesn't clump.
Now, they're not related to a neutron.
That's right.
They are related or
No,
they're
they're
not?
not.
You're right.
They just
They're not.
have a similar name.
They just have a similar name, yeah.
Did you know that a neutron is a combination of proton and electron? Right?
That's
They-
that's one way to make them.
Yeah.
Oh, okay.
Nuanced, too.
All right, that's two of them down. You do the honor, taller young man. Well, unless you got anything more to say about it. I don't know that there is no relationship between dark matter and dark energy. They're
No.
two separate entities.
Yeah.
One of them is getting us together and keeping us together, the matter. The other is making us fly apart. And that part we may address on this next one.
Dark energy, like used Jerry
Wait a minute,
Wilson's,
that's not it. There's a missing one.
dark matter, to use Jerry Wilson's simile, is really unknowing.
It's what?
Unknowing.
Oh, you just know it's there because it
Don't know him.
shows you its gravity. It doesn't show you electrical anything. There's no big lines of force. Okay. After the Big Bang, we have the smaller universe. You do this while you guys read. Here's the Big Bang. How many 14 billion years ago? Okay. And the universe for a few million years was this size? Is that what we've heard? It started as like a balloon? We've heard the old balloon thing, right?
It expanded rapidly, but it expanded super rapidly in like the first 10 to the minus 30 something
36
seconds. Okay, so it expanded, the space itself expanded faster than the speed of light. Otherwise, we would not have a clumpy universe. Everything would be like a uniform suit.
Yeah, okay, but suffice to say, back then, it was smaller, everything was
Yeah.
crammed in a smaller space.
Yeah.
Even though it was gigantic, than we are now, today, right?
Yeah.
Today, we're this big. And we're out here somewhere.
Well, no, we're in the center of it.
We're here?
Anywhere you are, you're at the center of the Big Bang. Because it created space.
Okay.
Everybody's the center of their own universe.
Here's the problem I have. If they keep telling us it's like an expanding balloon, and all the dots on the balloon are going apart from each other, right? Then, where's the edge of a balloon? Where's the edge of the universe? There is no edge. It's just-
If there is one, which there may be, it's farther away than we can see.
Okay, so everybody's in the center, not just us? If we were,
You are at the center of your universe, I'm at the center of my universe. I have 30 feet more I can see in that direction than you, and you have 30 feet more in that direction than you can see.
okay, well, what makes me wonder is, why can't we look to a certain place in our telescopes and say, that's where the Big Bang started? We can't.
Everywhere it is, because
Everywhere.
it's everywhere.
In 10 to the minus 32nd sentence, it went from a point to everywhere.
To like softball size.
Okay, but
Which is enough to
we
outspeed
can't
light.
nail down that point is not a place.
That's
It's
right.
every
Every
place.
place.
It's
Every
every
place.
place. It's not one place.
So everything is expanding right now. Is it expanding at the speed of light? Is that how fast they think we're expanding?
Maybe
That's
it's
why
way
light-
out there.
Light just doesn't
Well, it's,
bounce against the edge and come back?
okay, so the space between us and those things is expanding. So
Okay.
it's not like they're zooming away at the speed of light. I mean, they look like they are, but they're not zooming through their own space at faster than the speed of light. But from our point of view, they could look like they're going faster than the speed of light. Because if you're twice as, in a uniformly expanding space like that, if you're twice as far away, you appear to be moving twice as fast away from what you pick as your central point.
Okay. So if
But
we
you're
look-
still expanding at the same rate, right?
If we look back in time and across the universe 13 billion light years, which is the same as 13 billion years ago, and we see some early misshapen globs that became organized galaxies, wasn't the matter that is now us back there too?
Yes.
Yeah.
It was, then how?
We
How
can't,
did we get here? And are we gonna see what was us? Yes, ma'am.
That wasn't the matter that's in our galaxy, that was the matter that's in those galaxies.
That was the matter that was a couple of microns away before the big, it wasn't even matter then, but that was the part of space that was a few microns away from us when this fast inflation started.
Okay, but aren't they gonna reach a limit with the web or whatever that you're not gonna be able to see anything?
Well-
no more than 14 billion light.
oh, yeah.
Yeah, you'll reach the cosmic microwave background and that's all you can see, yeah.
And you're never gonna see an edge or,
Yes, that is the edge.
that is the edge.
That's the edge of what you can see.
13.8 billion light years.
Yeah,
That's
yeah.
Spatially.
beyond there hasn't reached us yet.
Adrian, you're drinking those?
Right, well, like you said, we can't outrun light, so.
Like I said.
Th- those-
The objects that are moving away from us faster than light, that light is never gonna reach us, because it would have to go faster than the speed of light.
Okay,
You can't do.
And the stuff you're seeing now, when we look at stuff that's near the edge of the cosmic microwave background, that's 12.5 billion light years away, that's look back time. We're seeing it the way it was 12.5 billion years ago. But it's actually, the universe has been expanding since then, so it's actually something like 50 billion light years away now.
It emits it out here, and then by the time light gets here, it's already moving.
let me see if I get that down. The universe as we know it, from the Big Bang to now, Big Bang there was nothing before, right? Just nothing.
Nothing.
Not even space. It's 14 billion, and yet you're saying it's been around for 50 billion?
No,
No.
What's
no,
been
it's
around
that
for-
far away now.
What's that, 50 billion light years?
Yeah.
The light that left there 13.8 or whatever, say 12 billion years ago, the spaces continue to expand, and the origin of that light is now out at 40 plus billion light years away.
Does science know how fast space expands? Can they put it in terms of
22
miles per hour?
22 kilometers per second per million light years.
Well, it's small.
Is that true?
So every
not, but it's very small.
Expand away from you 22.
Is that called the Hubble constant?
That's the
Yes.
Hubble constant.
But it's not really constant.
Yeah, that's a minor detail.
Yeah.
But because, look, you're talking about an expansion, so it's not one speed, right? I measure something, I measure a nearby galaxy, it's moving away from me at a certain speed. I measure a galaxy further away, it's moving away faster. It's gotta be moving away faster.
And
So
everything's
that-
speeding up too, right?
And then there's that too. That's
how
that's a correction on the whole thing.
That's the nasty
On top, yeah.
energy, right? Dark energy is
Yes.
causing that, right?
But just, if you wanna talk about how fast is the universe expanding, it's gotta be, well, how far away are you looking? It's always, give the distance, that will tell you what, and that's gonna, the speed's gonna be based on how far are you looking.
I understand the red shift, but it's gonna reach a point where there's no shift, right? If they're going, that's what we were just talking about. They're gonna go so fast, let's say if a galaxy's leaving away from us at half the speed of light, and we're going away from them at half the speed of light, that light's never gonna get to us, right? Or is that
Right, but
not?
that's a different thing than the redshift from the expansion.
Aren't some of the galaxies moving close to the speed of light? Are they going that fast?
It's
Careful.
moving through space.
There's a
Less
difference.
It's
Space is
expanding faster.
expanding with a minute.
There's a difference between a galaxy moving through space and space itself getting bigger. When we're talking about the Big Bang, we're talking about the expansion of the universe, we're not talking about a bunch of galaxies moving through space.
There's not
We're
gonna be.
talking about the space itself was stretching.
Okay. so
That's why it's a different problem. when you
There
get
won't be
into-
a big crunch.
Well, we
Doesn't
don't
look
know
like
for
it.
sure.
Doesn't look like
You think it can slow down or turn around? Denny, what do you think? My friend here has just joined, he's former
You have to
physics guy.
differentiate between the speed of light and the speed of the expansion of the galaxy. Within the space-time fabric, you can't go faster than the speed of light. But it itself can expand faster than the speed of light.
Yes.
And is it?
Yes.
Or did- I thought it did right after the Big Bang, it had to, or.
Yeah, that's that initial inflation, but now, places far from us, it looks that way too.
Yeah, they're finding, take your balloon, for example. If you're anywhere on the surface of that balloon and you look at things that are moving away from you, no matter where you are, they're all moving away at the same rate.
I know,
Well, if they're twice as far away, they're moving away
Oh,
twice as
exactly,
yeah, yeah.
exactly, yes, yes.
and that gave me the misapprehension that it was sort of a contained round ball. But it's not, it's everywhere, I guess. Are we growing, but we can't see it
No.
ourselves, or we're not?
We're not
getting
empty.
big? Huh?
We're not empty space.
Too much gravity around
Oh,
us.
it's just the empty space that we're in, we're staying the same size. All right, we want to eat in a few minutes, so let's.
Waistlines are expanding.
It's by the fact that like within the atoms, that we are basically empty space, so
This-
we're
but-
not expanding.
but we're bound in
Too much
that.
other forces,
Too much other
gravity and stuff like that.
This has always fascinated me. Probably started about 2001 Space Odyssey, about the second or third or fourth time I saw it, when I saw the two rotating donuts in space. And Kubrick wanted to be so accurate that he had the damn thing not even finished yet. You remember the frame of the donuts of the big rotating space station, and there were parts of it, and that's where he met with the Russians, and the floor was curved.
Yeah.
They now say he blew it by making it turn too fast, because he wanted to be able to see it, and the men and the people, just like on a merry-go-round at school, get thrown off. That's what centrifugal force, which would become our artificial gravity, or at least one of two ways of doing it in space. And so, I would have weighed on that space station with Kubrick 900 pounds, and 3 times. So, artificial gravity, am I correct? I just sort of came up with this. Two methods. One I call the increasing elevator effect. I'm not sure what they call it in science.
Constant acceleration.
A rocket, yeah, but it does take a constant power. Heading toward Alpha Centauri, just keep speeding up the rocket ship, you're on the bottom part of it, and you got gravity, but you burn up a lot of fuel, then halfway there you turn it around and slow it down. Okay, that's one good one, but my favorite is good old centrifugal force, which only needs the initial power, right, to get it going. It doesn't ever slow down, it doesn't run into friction in space. What was the movie, Passengers? What was the name of that movie where, what's her
Yeah.
name?
Chris Pratt and Jennifer Lawrence.
Jennifer Lawrence gets awakened by the guy, he wakes up or something. they're rotating on the way to a star. So, it dawned on me that your, artificial gravity would need a concave surface, right? Like that. And
So,
you're,
donut.
you're on the surface of gravity of the surface of a body in space, like Earth would be convex. Can you turn that over? So question, is it possible to spill your coffee? If you're on the inside, let me draw this, you probably know what I'm talking about here. Inside the rotating barrel, here's the astronaut drinking a cup of coffee. And would it spill down
Yes.
to the edge?
Yeah.
Because it's
Still radially.
Not straight down.
It wouldn't go straight down?
It'd be
No,
Coriolis.
because
Yeah. Oh, yeah.
if you think about how your velocity differs as you move farther out, on the edge of this circle, you're going a lot faster than you are in the middle, right?
Yeah.
You have a farther distance in between.
Right.
So that means, let's draw a bigger guy here. If this guy drops coffee from here,
Okay.
it's going to be traveling with a small velocity that way. Right?
Why wouldn't it go back this way? It does.
Well, it does to him, that's what he sees.
Oh,
But if we're looking at this from the reference frame that this is all rotating, then this is going to have an initial velocity pushing it that way, right?
and it would spill onto this and just stay
And
over
so, well,
coffee.
it would move something, well, it would just move in a straight line like that to us. But to the person inside here who's rotating, it is going to appear to fall backwards like that.
Okay.
Because he's constantly rotating into this line. And so for every point, it's going to be slightly lower and slightly backwards.
All right, well, I'm gonna dismiss the fact that you got two different scales here, and actually, at this scale, if that was a regular human, this sucker would have to really be turning.
Yeah.
If this was the scale, it'd be a little slower, okay, would you agree to that? And it'd still be pushed on the outside. Question number 2, bouncing a ball. Would he be able to throw the ball just like we do on Earth, curves, or would it go clear over here and bounce across? Go wild, crazy, be out of the.
So you could throw it, but you would have observed Coriolis
Coriolis
forces.
gets in the back.
Because
Coriolis?
when you're, yes,
What's that?
That's
what we just described.
so when you're in a non-inertial reference frame, which is what this is called,
Your space.
you have observed pseudo forces. So it looks like everything else has some kind of force on it, even though it really doesn't to an inertial reference frame. So when you throw something like that, you're giving it a velocity there, and to us, outside, not rotating, it's going to move
Straight.
in a straight line.
Not an arc.
No,
No.
because there's no, to us, there's no real force acting on this. So it would not deviate from its straight line velocity. But to this person who's rotating, he does observe a force. And in fact, he observes what we call Coriolis force, which is not really a force.
It's not really a force.
It's a pseudo force because it's a consequence of his rotating reference frame.
Coriolis,
He's going to see it.
C-O-R-R?
C-O-R.
C.
Oh, that-
LIS.
Coriolis, never heard of it.
And there are more complicated geometries involved, but conceptually, if you throw something like that, from your reference frame in here, it's going to appear to curve outwards, really.
Oh, gotcha.
Because he's going to rotate
Catch up
like
with
that,
it.
and it's,
Okay.
yeah, it's going to appear to curve like that. And in fact, that's why hurricanes in the Earth's atmosphere are in that spiral pattern. Because the Earth is a rotating reference frame. And so, if you just look at the top hemisphere, what a hurricane is a area of low pressure surrounded by areas of higher pressure.
Makes
Or
us-
maybe the other way around.
Makes us
So
spin.
the higher pressure moves towards the lower pressure. But since we're rotating, it lags behind a little bit and you get a
Oh,
rotation.
because of the turn of the
Surface
earth.
rotation.
Because the earth is rotating.
Yeah,
And it does it just opposite in the southern hemisphere.
that's right. The observed
Or
Coriolis
it's like one
force.
direction in Australia, another
The
direction.
observed Coriolis force.
Not toilets.
That's what that is.
Which is just being
All right, now inside this rotating drum, which is your artificial gravity, and you saw the scene in 2001 where they're running around on the inside. If somebody were up in here, they could just have the time of their life, couldn't they? Floating, right?
Yeah.
With the things going around it. So couldn't this guy get to that by running against the turn? This is the way it's turning. And if he could run fast enough and then jump, would he join the floating weightless people again, or
Well,
would
you
he
have to remember
come back down?
that the only force keeping him, pushing him this way is the normal force
The
of the
fact that he's
surface.
turning.
Yeah.
So when he stops turning and jumps up, there's nothing stopping him from just going all the way to the other side and hitting the other side.
Might there be a speed factor where it turns so fast that he couldn't run fast enough? In other words, to get his weight, it'd have to be, let's say, on a bicycle.
Yeah,
In
sure.
fact, I put that up there as the last part of it. If he rode a bicycle backwards, could he just, like at the end of
He
each
could ride it
scene?
forwards, just in the opposite direction it's turning.
Well, if he rode it in the opposite direction of his velocity and negated that velocity, then, yeah, like you say, there would be no centrifugal force on it.
Okay, fascinating stuff. Why don't they do it? Why aren't we cramming our astronauts against the bulkheads turning around as it goes around the Earth? We're letting them float and then they're losing their bone mass and coming back,
Very expensive to
Unhealthy.
make something big enough to do that.
yeah, it needs to be big enough.
And then you have to be able to dock with it.
Oh, well, then just slow it down and stop it.
The rotating seals in space are very difficult to maintain.
Rotating seals?
Seals, where you have a rotating part of the thing against the stationary part. You're gonna have to have
Oh,
a rotating seal that keeps the atmosphere inside. So not only beveling.
Okay, but now on the trip to Mars, they're gonna have to make some gravity, wouldn't you say?
Make the whole thing rotate.
Yeah.
But then you don't have a docking station, it's rotating too.
Okay. And have they figured out references as far as how fast versus how big versus how much you weigh to give you?
Right, definitely, yeah, that's a fairly simple
Then you
equation.
square over.
There's an
Yeah,
equation.
the acceleration, so if you think about Newton's, if you,
Qualifiers, here we go.
you have to think, you want your acceleration towards this surface radially outwards to be the same as the acceleration of gravity, right?
Yeah, right. You weigh 200 pounds, it's got to flatten you against the hull, 200
Yeah.
pounds worth.
So that means the change in your velocity from when you go from there to there
Oh, okay, got it.
has to be this acceleration, right?
G.
And you can calculate that to get that acceleration, you need to move at a velocity
Squared?
squared over
Every squared over R.
What's the R?
Radius.
The r is the radius of your.
From here? Really? They came up with that and that equals normal 1G?
That equals your acceleration. So
Oh.
you need to have this equal to g if you want
Yeah,
to,
1G.
if you want it to be simulated.
Wow, okay. I think you guys answered that. Any other questions on this? I don't know what I did on the last one, maybe. I think that's probably it. Shall we call it a night and eat? For a change?
Thank you, Professor Herron.
And if you're wondering why I talk so much about centrifugal force, I just read a lecture on it now.
That is the only way, right? That and the other method.
I mean, those are essentially the same, in the same vein. They're both non-inertial reference frames where you have constant acceleration.
What I called accelerating elevators, is there a word for that? A name that I don't know about? Having the rocket ship just keep it.
Constant acceleration.
That was his thought, that's how he said gravity is an acceleration. You can't differentiate between the force of gravity and acceleration. He put his person in an imaginary elevator that was always increasing its speed at constant acceleration. There's no test you can perform inside that elevator that says you're not on a planet with that.
Well, I gotta tell you something, Bruce, I read once in Ripley's Believe It or Not, I think it's pretty accurate. Einstein said, we're not falling to the earth is rushing up to meet you.
The earth sucks.
See,
Okay, well then, if there are no more questions, we shall open up for refreshments. We have a lovely spread here, full of fruits, egg rolls, cookies.
Bruce, would you lead us through, please? Gluten-free, I'm sure.
No, I'm diabetic.
That's all sugar.